There is a structure sitting in a river valley somewhere near you that holds back more water than most cities use in a century. It does not move. It makes no sound. It has no engine, no moving parts in its primary structure, and no active mechanism keeping the water from flowing through it. It is, in the most literal sense, just a wall. And yet behind that wall sits a volume of water so large that if it were released all at once, it would erase everything downstream within hours. The question of how a dam works sounds simple. The answer is not, because a dam is not just resisting water, it is managing pressure, seepage, uplift, thermal expansion, seismic loading, and its own weight simultaneously, every second of every day, for a design life measured in centuries. And when that management fails, it fails without warning. Start with the scale. The Three Gorges Dam in China is the largest hydroelectric dam in the world by installed power capacity. Its reservoir holds approximately 39.3 cubic kilometers of water. 1 cubic kilometer of water weighs 1 trillion kilograms. The total mass of water held behind the Three Gorges Dam is therefore roughly 39 trillion kilograms, or 39 billion metric tons. The dam structure itself is 2,335 meters long and 185 meters tall. The concrete in its body weighs around 27 million metric tons. This is not an unusual scale for a major dam. The Hoover Dam on the Colorado River holds back Lake Mead, which at full capacity contains approximately 36.7 cubic kilometers of water. The Itaipu Dam on the Brazil-Paraguay border displaced so much mass when its reservoir filled that seismologists detected measurable changes in the local gravitational field. The first thing to understand about how a dam resists this load is what the load actually is. Water exerts pressure in all directions, but the relevant pressure for a dam is the horizontal hydrostatic pressure pushing against the upstream face. This pressure is not uniform. It increases linearly with depth. At the surface of the reservoir, the pressure on the dam face is zero, or more precisely, it equals atmospheric pressure, which is the same on both sides and therefore produces no net force. At the base of the dam, the pressure is equal to the density of water multiplied by the gravitational acceleration multiplied by the full depth of water. For a dam holding back 180 meters of water, the pressure at the base of the upstream face is approximately 1.76 megapascals, or about 17.6 times atmospheric pressure. Integrated over the entire upstream face of the dam, this produces a total horizontal force that must be resisted by the dam structure. There are two fundamentally different ways to resist this force, and they correspond to the two primary types of large dams. A gravity dam resists the horizontal water pressure through its own weight. The dam is made massive enough that the downward force of its own weight, acting through its base, creates a friction force against the foundation rock that exceeds the horizontal force of the water. The geometry is critical. The dam must be wide enough at the base that the resultant of the water pressure force and the dam's own weight vector passes through the middle third of the base. If the resultant passes outside the middle third, the upstream edge of the base begins to experience tensile stress. Concrete is strong in compression but weak in tension, and a dam foundation that goes into tension will eventually crack and fail. Gravity dam design is fundamentally an exercise in ensuring that the resultant force stays within acceptable limits under all loading combinations, including full reservoir, partial reservoir, earthquake loading, and temperature effects. An arch dam works on a completely different principle. Instead of using mass to resist the water load, an arch dam transfers the horizontal water pressure into compressive stress within the arch, which is then transmitted into the canyon walls on either side. The arch shape means that the water pressure, which acts perpendicular to the upstream face, is resolved into compressive forces that run along the curve of the arch toward the abutments. Stone and concrete are extremely strong in compression. An arch dam can therefore be much thinner than a gravity dam for the same height and reservoir depth because it does not need to be massive, it needs to be geometrically correct. The Hoover Dam is a combination arch gravity type, using both principles simultaneously. Pure arch dams such as the Vajont Dam in Italy or the Gordon Dam in Australia are dramatically thinner relative to their height, with crest thicknesses that seem impossibly slender for the loads they carry. But resisting the horizontal water pressure is only one of the structural challenges. There is a second force that is less intuitive but equally important. It is called uplift pressure. Water does not only push against the upstream face of a dam, it also seeps into the foundation rock beneath the dam and into any cracks or pores in the dam body itself. This seeping water is under pressure. At the base of a dam, the upstream water pressure acts downward on the foundation, but it also acts upward on the base of the dam structure through the saturated foundation rock. This upward pressure, called uplift, directly reduces the effective weight of the dam that is available to resist sliding. If uplift pressure is not managed, a gravity dam that was designed with adequate safety margins against sliding might find those margins eliminated by the upward force of water seeping beneath it. Dam engineers manage uplift through drainage systems. A series of drainage holes are drilled through the dam body and into the foundation rock, typically at intervals of a few meters along the base of the dam. These holes allow seeping water to escape at lower pressure rather than building up to full hydrostatic pressure beneath the structure. The drainage water is collected in inspection galleries, tunnels built into the interior of the dam that allow engineers to walk through the structure, monitor seepage flows, measure crack widths, and inspect the condition of internal drains. The flow rate from the drainage system is continuously monitored. An increase in seepage flow is an early warning sign that something is changing in the foundation or the dam body, and it triggers investigation before a problem becomes critical. Seepage through the foundation is also managed by a grout curtain. Before and during construction, holes are drilled deep into the foundation rock upstream of the dam, and cement grout is injected under pressure to fill fractures and permeable zones. This creates a barrier that reduces the rate at which water can migrate through the foundation toward the downstream side. The grout curtain is not perfectly impermeable. Some seepage always occurs, but it reduces the seepage to a rate that the drainage system can manage safely. Temperature is another loading condition that most people never consider. Concrete expands when it is warm and contracts when it is cold. A large concrete dam is not a uniform temperature throughout. The exterior surfaces respond to daily and seasonal temperature changes while the interior of the massive concrete body remains at a much more stable temperature. This temperature differential creates internal thermal stresses. During the curing of the concrete during construction, the chemical reaction of cement hydration generates heat. In a massive concrete pour, this heat cannot escape quickly, and the interior of the concrete can reach temperatures 30 to 40 degrees Celsius above the exterior. As the interior eventually cools, it contracts, but it is now restrained by the already cooled exterior. The result is tensile cracking in the concrete interior. To manage this, the concrete in large dams is placed in blocks separated by contraction joints, vertical planes of weakness that allow each block to shrink independently without cracking. Low-heat cement formulations are used to reduce the peak temperature during curing. In some projects, cooling pipes are embedded in the concrete during construction and cold water is circulated through them to accelerate heat removal. After the concrete has cooled to its stable temperature, the contraction joints are grouted under pressure to bond the blocks together into a monolithic structure. The Hoover Dam used all of these techniques. Without them, the thermal cracking in the dam body would have been severe enough to compromise its structural integrity. Seismic loading adds another dimension to the design problem. A dam situated in an earthquake zone must be designed to resist not just the static water pressure but also the dynamic forces generated when the ground accelerates during a seismic event. The water in the reservoir also responds to ground motion. When the dam accelerates upstream during an earthquake, the water pushes back with an additional hydrodynamic force that adds to the static hydrostatic pressure. This is called hydrodynamic pressure, and it was first analyzed systematically by the engineer Westergaard in 1933. Modern dam earthquake design uses detailed dynamic analysis, including the response of the dam structure, the foundation, and the reservoir water as a coupled system, to determine the forces the structure must resist under the design earthquake. Earthfill and rockfill dams, which together make up the majority of dams worldwide by number, work on yet another principle. They do not resist the water load through structural action the way a concrete dam does. Instead, they work by mass and by the principle that a sufficiently wide embankment of compacted soil or rock will not allow water to flow through it fast enough to cause failure. The upstream face of an earthfill dam is typically covered with a less permeable material such as clay or a geomembrane to reduce seepage. The interior of the dam contains a filter and drainage system that collects any water that does seep through and removes it safely without allowing it to carry away soil particles. The removal of soil particles by seeping water, called internal erosion or piping, is the primary failure mechanism of earthfill dams, and it is insidious because it can progress for hours or days before becoming visible at the surface. The Teton Dam in Idaho failed in 1976 due to internal erosion. Water seeping through the foundation and the contact between the dam body and the canyon walls gradually eroded soil particles, creating a pipe of increasing size through which water flowed at increasing velocity, removing more material, enlarging the pipe further in a self-accelerating process. The dam failed within hours of the first visible signs appearing on the downstream face. 11 people died, and the economic damage exceeded $1 billion in 1976 values. The failure investigation found that the design had not adequately addressed the permeability of the foundation rock and the difficulty of compacting the soil fill against the irregular canyon walls. This is why dam safety monitoring is not optional and not routine in the way that a car inspection is routine. Large dams are instrumented with hundreds of sensors measuring settlement, horizontal movement, pore water pressure in the foundation, seepage flow rates, crack widths, and temperature. These measurements are taken automatically and continuously, and the data is reviewed by engineers who understand what normal behavior looks like and can recognize deviations that indicate developing problems. The first line of dam safety is design. The second line is construction quality. The third line is continuous monitoring, and the fourth line is the emergency action plan that specifies exactly what actions will be taken and in what sequence if the monitoring data indicates that failure may be imminent. A dam does not hold back billions of tons of water through brute force alone. It holds it back through geometry, drainage, material selection, construction technique, and continuous management of forces that never stop acting. The wall looks passive. The engineering behind it never is. And that raises a question worth sitting with. If monitoring can detect a developing failure in advance, why do dam failures still happen without warning? The answer involves the gap between what sensors measure and what actually causes failure, and it is more uncomfortable than most official accounts suggest.